Let's apply what we were just talking about with respect to stoichiometry of chemical reactions in the gas phase to make a prediction about a chemical reaction that involves a gas phase product. This is example 8.19 in your Openstax textbook. And what we're going to do here is we're going to combine some of the skills you picked up in Gen Chem 1 along with what we now know about gas phase behavior and the ideal gas law to make a basic prediction about product yield in a chemical reaction. The twist is going to be that in this case, our product is going to be a gas. And so essentially what we're going to do here is a theoretical yield calculation where the limiting reactant is identified. But now we're going to bring in the ideal gas law so that when we're talking about the yield of our product, which is a gas, we are not going to talk about it in terms of grams or percent yield. We're going to talk about what volume of the gas are we going to collect. The question setup is this. For the balanced chemical equation below, where 2 moles of solid gallium, a close cousin of the element aluminum, 2 moles of solid gallium react with 6 moles of aqueous hydrochloric acid in water. This makes 2 moles of the aqueous salt gallium chloride, which is water soluble, and then 3 moles of hydrogen gas, H2. If this reaction is run at 27 degrees Celsius and an external pressure of 723 torr, what volume of hydrogen in liters may be prepared by the reaction of 8.88 grams of gallium with an excess of hydrochloric acid? So there's a lot going on in this problem. We have to think through the information that we've been given carefully. The idea here is that we're asked about a volume of hydrogen that we're going to produce as a result of this reaction. So we're being asked about the yield of a gas phase product. Prior to learning about the ideal gas law, we would know how to use reaction stoichiometry, theoretical yield, identification of the limiting reagent to predict how many grams of hydrogen gas we would prepare. But because we're making gas phase product, we're going to talk about the amount of gas in terms of its volume rather than its amount in grams. So our overall strategy is going to be we are going to figure out how the moles of hydrogen produced can be related to the volume through the ideal gas law, PV equals nRT. We will first determine how many moles of hydrogen we expect to produce using our typical setup for predicting a theoretical yield in a limiting reactant situation. So we're going to say, look at our chemical reaction setup. And remember, you can't identify the limiting reactant directly from the balanced chemical equation. You have to have a stoichiometric argument for which reactant is in excess, or the excess reactant and the limiting reactant have to be identified for you in the problem. In this case, we're told that we have 8.88 grams of gallium, and we're told that we have an excess of hydrochloric acid. If we have an excess of hydrochloric acid, then gallium must be the limiting reactant, and our theoretical yield of hydrogen will be based on the mass of the gallium, 8.88 grams. So this will harken back to some of the Gen Chem 1 material where you talked about limiting reactant and theoretical yield. The idea is if we know the molar mass of solid gallium, we can figure out how many moles of gallium we have in 8.88 grams. And so what we're going to say is I'm going to first convert the grams of gallium to moles of gallium by dividing by the molar mass. Once I know the moles of gallium, which is the limiting reactant, I can predict how many moles of hydrogen gas I'm going to make based on the reaction stoichiometry. So 8.88 grams of gallium divided by 69.7 grams of gallium will give us the moles of gallium that enter the chemical reaction. Our balanced chemical equation says that we are going to produce 3 moles of hydrogen gas for every 2 moles of solid gallium that go into the reaction. We have a stoichiometric coefficient of 2 here for gallium and 3 here for our hydrogen gas product. If we follow the math, 8.88 divided by 69.7 times 3 divided by 2, we expect to make 0.1911 moles of H2 as a product. What the problem is really asking us to do is use the ideal gas law now to determine how much volume 0.1911 moles of hydrogen gas would occupy. And we know how to do that with the ideal gas law. We'll rearrange the ideal gas law to solve for volume, which will be nRT divided by P. And in setting up our out calculation, the only other thing we have to make sure is that we are in the correct units, which right now we are not quite, because our temperature is in degrees Celsius and our pressure is in torr, which is a measure of pressure that we've discussed a little bit before is roughly equivalent to millimeters of mercury. So to get our ideal gas calculation to work, we need to convert temperature to Kelvin and pressure in torr to atmospheres. I haven't shown the conversion here. I would encourage you to do that one for yourself. Remember to add 273 to the temperature to get your temperature in Kelvin. And remember that there are 760 torr in an atmosphere. So remembering that, I get an atmospheric pressure of 0.9513 atmospheres and a temperature in Kelvin of 300 Kelvin. The volume the hydrogen gas is going to occupy is now calculated as 0.1911 moles times 0.0821, the gas constant, times the temperature in Kelvin, 300 Kelvin, divided by the pressure in atmospheres, 0.9513. Moles cancels with moles, Kelvin cancels with Kelvin, atmospheres cancel with atmosphere, leaving us with the volume in liters. And we would expect that the hydrogen produced would occupy 4.95 liters under these pressure and temperature conditions. So this is kind of typical of predictions about gas phase reaction chemistry. The key thing to remember is that the ideal gas law is the way you link either a pressure or a volume measurement for a gas to number of moles. Once you know number of moles, you can use all the tools you've developed before that allow you to make predictions about a chemical reaction that involves a gas, theoretical yield, identifying limiting reactants, etc., to make predictions about gas phase chemical reactions. But for gases, it's the ideal gas law that allows us to link the amount in moles of the gas to a pressure or volume